Algebra begins with the fundamental concept of using symbols to represent numbers. These symbols, often letters like x, y, or a, are called variables. They stand in for unknown values that we aim to find. Alongside variables, we have constants, which are fixed numbers like 2, 5, or -7. When variables and constants are combined using mathematical operations such as addition, subtraction, multiplication, and division, we get expressions. For example, 2x plus 3. If we place an equal sign between two expressions, we form an equation, like 2x plus 3 equals 7. Solving an equation means finding the value of the variable that makes both sides of the equation equal. In this case, we subtract 3 from both sides, getting 2x equals 4, and then divide by 2 to find that x equals 2. This step-by-step process relies on understanding the order of operations, often remembered by the acronym PEMDAS. Linear equations. A linear equation is an equation where the highest power of the variable is 1. These equations graph as straight lines, which is why we call them linear. The standard form of a linear equation is y equals mx plus b, where m represents the slope of the line and b is the y-intercept, the point where the line crosses the vertical y-axis. The slope tells us how steep the line is. For example, if m equals 2, the line rises by 2 units for every 1 unit it moves to the right. If the slope is negative, the line goes down as it moves to the right. Understanding this concept allows us to interpret graphs and predict trends, which is especially useful in real-life applications like economics, physics, and data analysis. Linear algebra also includes solving systems of linear equations, which means finding values for variables that satisfy more than one equation at the same time. For example, in two-variable systems like 2x plus y equals 10, x minus y equals 4. We aim to find the values of x and y that make both equations true. There are 3 common methods to solve systems. Substitution, where we solve one equation for a variable and substitute it into the other. Elimination, where we add or subtract equations to eliminate a variable. And graphing, where we plot both equations and find their point of intersection. Quadratic equations, equations where the highest power of the variable is 2. The general form of a quadratic equation is where a, b, and c are constants, and a does not equal to 0. Unlike linear equations, which graph as straight lines, quadratic equations produce parabolas, U-shaped curves that can open upward or downward, depending on the sign of a. These curves appear frequently in physics, engineering, and even economics, often modeling scenarios involving acceleration or area optimization. There are several methods to solve a quadratic equation. One common method is factoring, where we break the expression into two binomials, like turning x squared minus 5x plus 6 into, which gives solutions x equals 2 and x equals 3. Another method is completing the square, which transforms the equation into a perfect square trinomial. When factoring isn't possible, we use the quadratic formula. This formula can solve any quadratic equation, regardless of whether it factors nicely or not. Quadratics are part of a broader class of expressions called polynomials, which are sums of terms involving variables raised to whole number powers. For example, is a polynomial of degree 2. Higher degree polynomials, like cubic and quartic, involve powers of 3, 4, and beyond. Understanding polynomials and quadratics is crucial, as they bridge the gap between basic algebra and more advanced topics like calculus and real-world modeling. Exponents and radicals, which deal with repeated multiplication and its inverse, root extraction. An exponent tells us how many times to multiply a number by itself. For example, x cubed means x times x times x. Exponents are used extensively in both mathematics and science to express large numbers, powers of 10, and exponential growth processes, such as population increase, radioactive decay, and compound interest. To work efficiently with exponents, we use a set of exponent rules. For instance, when multiplying terms with the same base, you add their exponents. When raising a power to another power, you multiply the exponents. When any non-zero number raised to the power of 0 equals 1, and negative exponents represent reciprocals, such as, on the flip side, radicals, also known as roots, reverse the process of exponentiation. The square root of a number, for example, is a value that, when multiplied by itself, gives the original number. So square root of 9 equals 3, because 3 squared equals 9. We also encounter cube roots and higher order roots, like cube root of 8 equals 2 or 8 equals 2 cubed. Simplifying radicals, combining like terms, and rationalizing denominators are key skills in this area of algebra. Exponents and radicals appear throughout all levels of math and science. They help us represent very large or very small values in a compact way, and are essential for progressing into topics like logarithms, scientific notation, and higher-level algebra. Functions and relations, which allow us to model relationships between quantities in a precise, mathematical way. A relation is simply a set of ordered pairs, inputs and their corresponding outputs. A function is a special kind of relation, where each input has exactly one output. This idea might sound simple, but it's incredibly powerful. In everyday terms, think of a function as a machine. You feed in a value, input, and it gives you a result, output, based on a rule. Functions are typically written using function notation, like f of x equals x squared plus 3x minus 4. Here, f of x represents the output when we input a value for x. For example, if x equals 2, then f of 2 equals 2 squared plus 3 times 2 minus 4, which equals 4 plus 6 minus 4, which equals 6. This notation allows us to clearly communicate and evaluate expressions. Two key ideas associated with functions are the domain and range. The domain is the set of all possible input values, usually x values, while the range is the set of all possible outputs, y values. Understanding these helps determine where a function is valid and what kinds of results we can expect. There are many different types of functions you'll encounter in algebra: linear functions, quadratic functions, cubic functions, exponential functions, and absolute value functions. Each has a unique graph and behavior, and learning to analyze and sketch these graphs is a fundamental skill. Mastering functions gives us the ability to describe patterns, make predictions, and understand complex relationships, making this one of the most important concepts in all of algebra. Exponential functions. These are functions where the variable is in the exponent, such as f of x equals 2, raised to the power x. Exponential functions are used to model rapid growth or decay, like population increases, radioactive decay, or interest accumulation in a bank account. Logarithms, which are the inverse of exponential functions. A logarithm answers the question, to what power must a base be raised to produce a certain number? For example, log base 2 of 8 equals 3 because 2 raised to the power 3 equals 8. Logarithms are useful in solving equations where the variable is in the exponent and are widely used in fields like acoustics, seismology, and computer algorithms. Sequences and series are also part of advanced algebra. A sequence is an ordered list of numbers following a specific pattern, such as an arithmetic sequence where each term increases by the same amount, or a geometric sequence where each term is multiplied by a fixed value. A series is the sum of the terms in a sequence, and understanding how to work with them helps solve problems involving repeated or accumulating patterns. Matrices, which are rectangular arrays of numbers used to organize data and solve systems of equations more efficiently. They also play a crucial role in linear algebra, computer graphics, and machine learning. At the highest level of algebra, we enter the world of abstract algebra, a branch of mathematics that explores algebraic structures in a more theoretical and generalized way. Unlike the earlier stages of algebra, which deal with numbers and equations directly, abstract algebra studies the rules and systems behind those numbers. This includes concepts like groups, rings, fields, and sets. A group is a set of elements combined with an operation that follows 4 basic rules: closure, associativity, an identity element, and inverses. For example, the set of integers under addition forms a group. Groups are used to study symmetry, both in mathematics and in real-world applications like physics, chemistry, and even music theory. A ring is another algebraic structure that extends the concept of a group by including 2 operations, typically addition and multiplication, that interact in specific ways. A field goes even further, adding properties that make division possible, except by 0, making it the most structured of these systems.